Welcome to the exquisite world of EMR, electromagnetic radiation. What you're seeing on the screen is the best we can do in terms of a visual representation of an electromagnetic wave. And what you're seeing is perpendicular bands of an electric field and magnetic field. So the electric field and the magnetic field are perpendicular to one another. And we learned in the last unit that a changing magnetic field will create a changing electric field. And of course, that changing electric field will in turn create its own changing magnetic field. Hence, you get electromagnetic radiation. Okay, and as you can see, they're perpendicular to one another, and the direction of the travel direction of the wave is perpendicular to that. So it's acting in 3 dimensions. This electromagnetic wave, though, will radiate 360 degrees in every single direction. Okay, so let's go through your notes. You can read through. They're pretty straightforward. Let's just point out some highlights. Electromagnetic radiation is the way that energy can be transferred. That's pretty darn important. And then it talks about alternating fields as essentially act as transverse waves. Let's just review what transverse waves are. Transverse waves are waves that look like this. In other words, the wave is perpendicular to the direction of travel, as opposed to a longitudinal wave. Longitudinal waves, remember when we did slinkies in Physics 20, and then you compress the string here, and the longitudinal wave travels, so the direction of travel is parallel. The transverse waves is perpendicular. And it says they radiate outwards in all directions. EMR, electromagnetic radiation, travels at the high velocity of 3 times 10 to the 8th meters per second, which of course is the speed of light. And the most recognizable form of EMR is obviously one that we can see. It's the only one we can see. It's called visible light. All the other forms of EMR, we can't see them. Okay, then the next part of okay, this is an important part right here, though. Although electromagnetic radiation has the same velocity, it has they come from different sources. They have different frequencies and different wavelengths, but the different sources all involve very important accelerating charges. So you have a charged particle, it's accelerating. It's going to give off some form of electromagnetic radiation, depending on the frequency or the wavelength of that charge. EMR can be detected indirectly or directly or indirectly. Again, you can read all this. And then we go through, let's go to the EMR spectrum. We have our universal wave equation, which we're now going to change. The universal wave equation you learned in Physics 20. It says velocity equals the frequency times the wavelength. We're just going to change the velocity to c, because c represents the speed of light. And it's always going to be 3 times 10 to the 8th meters per second, which is, so you're impressed by this number, which is 300,000 kilometers per second. 300,000 kilometers in 1 second. And yet it takes light 8 minutes to go from the sun to reach the Earth. So that shows how far away the sun is. And in grand scale of the universe, the sun is extremely close to us. The next part of your notes goes through all the different forms of electromagnetic radiation, and I'm not going to go through these. You can read through them. We start with low frequency alternating currents, then we go to radio and radar, microwaves, infrared, visible light. You need to know this, Roy G. Biv. I'm sure you learned that in grade 2 or something. Roy G. Biv, need to know that. And then it talks about also how each of the forms of EMR is what causes them. Let's just take one of them, for example. So it says visible light happens when electrons make big jumps around energy levels in atoms. So if you've got an atom and you've got all these electrons going around it, this electron decides to go from this level to this level, it jumps from this level to this level, it will give off some electromagnetic radiation, and you may be able to see that in the case of visible light, or if it's a higher frequency like ultraviolet, you may not be able to see it, but it's still there, it still exists. Here's another thing that you should know. You should know that in visible light, the wavelength or the frequency, now let's go with wavelength. I like talking about wavelength. The wavelength of red light is about 700 nanometers, nm. 700 nanometers, and green is 500 nanometers, and violet is around 350. Blue is around 400 nanometers. So that's the wavelength, and obviously the as you increase in wavelength, you're decreasing in frequency. So electromagnetic radiation that has a high wavelength, a really long wavelength, has a very low frequency. And we'll talk more about that later. Then it talks about ultraviolet radiation, and as you can probably surmise, as we go further along the electromagnetic spectrum, these ones are getting more and more dangerous. For example, let's just go back for a second. We are constantly being bombarded by radio waves and microwaves and infrared radiation and visible light, and they don't really harm us anyway. But what ultraviolet radiation, that can be a little harmful. You don't want too much. That's why you put sunscreen on. X-rays, you definitely don't want to be too exposed to X-rays all the time. That's why you wear a big iron or lead vest when you have X-rays done at the dentist. It's to protect you from the electromagnetic radiation. You're going to get a dose of it, but it's a very low dose. They just put the lead thing on you to prevent your main torso from getting bombarded by X-rays. And then gamma rays and cosmic rays, which get increasingly dangerous. If you get bombarded by a lot of gamma rays, then pretty much done. And then there's just, I've got some diagrams here that you can look at. So here is what the electromagnetic spectrum looks like. In this one, we've got increasing frequency. So radio waves start here, and then this symbol here looks like a Y is gamma rays. And it gives you the approximate frequency of all the EMR, and then at the bottom here, it gives you the wavelengths. And you don't really have to memorize them, but you should have, kind of vague indication or a vague idea of what frequencies belong to each type, and so on. And that is it. Again, here's Roy G. Biv. If you were writing a diploma exam, it would be expected that you would know the wavelength of red light and the wavelength of green light and violet light. Not all of them, but a few of them. And then I've got another picture here. Again, just showing what the electromagnetic spectrum looks like. And this is a little more practical. As you can see here, it tells you what the wavelengths are. Some of these wavelengths, for example, a soccer field. When we get over to here, those are radio waves. When we get over to microwaves, it's more the size of a period. Infrared, the size of a cell, the wavelengths. And then gamma rays here. I mean, yeah, they don't even have a picture for that because they're so small. And then the frequencies, or what causes the source of the electromagnetic radiation. Obviously, a radio wave is caused by AM amplitude modulation radio. And then we have FM here. We have microwaves caused by a microwave oven, radar, and so on. So this is a good one to give you a more practical sense of electromagnetic radiation. And just another little picture there. And that pretty much concludes the introduction to electromagnetic radiation. Okay, on to the next lesson.